Hello everybody, this is lecture number 33 and we are into chapter 9, okay, and we are studying 2D elasticity problem. Okay, so we have studied the strong form first, okay, that was in lecture 31, and then from there we derived the weak form. So that was in the last lecture video. Okay, so weak form, what we got? So in the last lecture video, weak form was something like this. So we have gamma t, and then we had w tilde transpose t tilde d gamma, then minus omega, then here we had del s, then w, okay, so like this is also tilde, and transpose of that, and then we had sigma, okay, tilde, and d omega plus w transpose and b tilde d omega is equal to 0. So this is what the weak form is, where w is equal to wx and wy, that is what it means, yeah, okay, and b tilde means bx by similarly, okay, sigma tilde means sigma xx, sigma yy, and sigma xy, okay. Then del s, this one means, so we can write, okay, so okay, this t tilde means, so this is tilde only, so is equal to tx and ty, okay, we can say this is a bar, basically this is one given. Then del s is given as, so again, so this is working on w, so w is 2 by 1, so this is 3 by 2, del s 3 by 2, so this is so this one is like this, del over del x, okay, 0, del over del y 0, del over del x, del over del y. So this is what the del s is, okay. Okay, so all, so we know this now, this, the sigma tilde is not, w tilde, b tilde, so all of them are known now. Okay, so next is basically we have to find out the solve it, okay, but not yet, because we have to also we don't see u yet, right. So we have to somehow, we have to put u somewhere. W, if you see, this is coming from the weight, so no u here. T also, this is a given quantity, yeah, so there is no u coming here. This is some operator, some derivative of w, so no u here. Sigma is the one which will have u, yeah, so we will see how, and WB all are, this is also does not have u, and this also is given, this is body force. Yeah, so this that means sigma, we have to find out the sigma as a function of, so this sigma as a function of u, right. Okay, so we just write, okay, so let us u tilde only. So where u tilde means, so u tilde means ux and uy. So this is a function, we have to find out how a stress depends on the displacement and how to find out. Okay, so for that we have to, first we have to find out the strain, how the strain is related to stress. Okay. So remember, this is 2D elasticity, 2D elasticity, and in 2D elasticity basically here you can assume the material properties, either you will say this will be a plane stress problem, yeah, or it will be plane strain problem. Okay. So what is the difference? Difference is, in this case there is no third stress, this all the stresses are in the planar, means there is no out of plane stress. Yeah, so hence this is plane stress. In this case plane strain means there is no strain perpendicular to the plane. Yeah, so this is plane strain is. So again these things are not new. So this is in you have already studied these things during your solid mechanics classes. Yeah, so here for plane stress we will see, okay, how the relationship is, means for plane stress how a stress is depends on a strain. So there is a relationship that we will find out. So the idea is to relate like a stress depends on a strain, and which depends on u. Yeah. So this is the relationship. So basically what typically, for example, Hooke's law or generalized Hooke's law. So this Hooke's law actually tells us that sigma is proportional to a strain, and that is equal to d, this tilde strain E. Yeah. So where this is a strain, okay, strain matrix or a strain, actually we are going to write a strain vector, or maybe we just write is a strain this is equal to del ux over del x, del uy over del y, and del ux over del y plus del uy over del x. Okay. So this is the what the relationship is. Yeah, I mean how a strain is. This is what the strain is. Yeah. Okay. Or we can say that a strain is equal to. We can also write like this. How? So we will have u here, so write ux and uy, right? So anything there, okay. And then we have a strain, yeah, a strain. So we have ux, so write del over del x, yeah, and then you will have a 0 here. Then we have 0 del over del y, yeah, and then we have del over del y and del over del x. So, basically we can also say that really means this is simply is equal to. So, what we called it, this one we call it as, so see here we call that is at, so this is 3 by 2, yeah. So, this is 3 by 2 and we called it at del S, yeah. So, we call it del S. So, this is nothing but del S S E, okay. So, this how sorry not E but U, sorry. So, this is U. So, this is how the relationship is, right. Okay. So, we have got, so we have got this part how a strain depends on displacement. So, this is called a strain displacement relationship, yeah. So, this is called a strain displacement relation, yeah, okay. So, what you see, this is linear basically, what you see is it is not non-linear, this is a linear, hence we are studying the linear finite element. So, we are also doing the linear finite element only, okay. So, this is a linear relationship, okay. So, this is the strain displacement relations. Now, second thing is the we are going to use the Hooke's law, okay. So, this one, so what is the, we know what the strain is and the strain depends on the displacement like this one. Next thing is what is the stress is, what is the value of D and how this is related to this one. Now, we know that what is the meaning of this, yeah. This also this strain we also know as epsilon xx, epsilon yy and epsilon xy, which is equal to we have seen here del ux over del x, right, del u y over del y and del u x del y plus del u y over del x, okay. So, this we know already or we can also derive basically. So, if you see let us say this is the domain where we are interested and we have one control element from here. So, you have like this and then what you have done, you have applied a stress. So, let us say you applied the sigma xx, okay. Okay. So, basically here not sigma xx, let us say we have the displacements, okay. So, displacement is something like this. So, okay. So, let us say displacement here is ux, displacement here that will be del ux, sorry ux plus del ux over del x times dx. This is the displacement, yeah. Length is, what is this length? Length is dx, right. So, a strain epsilon xx will be what? Will be equal to change in length, right. So, change in length will be what? See here displacement is ux, here displacement ux plus this much, right. So, change in the displacement will be, or change in length will be what equal to dl over L, right. So, what is dl? dl is basically dl will be equal to dx, right, plus the difference between this and this minus dx. So, change in length will be simply equal to this minus this is the change of length. So, before applying the force it was dx, after applying the load this moves by ux, this moves by ux plus del ux over dx times dx, and hence the change in length will be this minus this, which will equal to just this. So you get del u x over del x times dx over dx is equal to del ux over del x. Yeah. So epsilon xx equal to del ux over del x. Yeah. So we got that. Similarly, we can get this one, the same argument, and we can write epsilon y is equal to del u y over del y. So we can give same arguments. So you have u y here u y plus del u y over del y times dy, right. So we can have like this, and hence we can derive like this. Next thing is like obtaining, how do you get this one? So all those things are already you have studied in solid mechanics, but I am just repeating for those who have not studied solid mechanics. Okay. So now the last one, like epsilon xy. Okay. So how do you find out this one? So basically this comes from this is the shear strain. Okay. So say, let us say you have the control elements, let us say you have the just this one, for example, this one element that we have taken from here. So what we are going to do is now fix at the bottom. So let us fix it like this, and you are applying a given a displacement here. Okay, given a displacement here by what? So we will have like this. So let us say the displacement here is ux, and here it will be ux plus. So we do not have to assume it is fixed here actually. So we can also have we just write the displacement, rather displacement here is okay. So displacement here is ux, okay, and displacement here will be what? Will be equal to, so that will be equal to ux plus del ux over del y dy, where of course this distance from here to here is dy, and hence it is like this, distance from here dx. Okay. So this is how the displacement will be. Okay. So that means after we have applied displacement, which is like this one, you will see that these points will move in this direction. So if this is moving by ux, this is moving by mode, that means this will not be vertically up, this will go something like this one. So actually this will be something like this, yeah. Okay. So this is how it will be, yeah. Okay. And this is what this is the angle theta, yeah, or we let's call okay, this is angle theta, and this theta is very small actually, yeah. So in this case epsilon xy is equal to just theta. So this is how we define the shear strain, yeah. However, remember that displacement is not just in one direction, displacements are also given this way also. So meaning that we have u and del u y is also there. So let us apply both the displacement from both the direction. Then what we will have? We will have something like that. Scenario will be like this and like this Yeah, so something like this, like this. I'm like exaggerating, so like this one and like this one. Okay, so that means we will have two angles, right? So we will have a theta 1 here, and this way we will have theta 2. Yeah, okay. So then how to find out? So basically this one, the way we found out, this one is ux plus del ux over del y times dy, and hence the angle here, okay, I forgot to write the angle here. So epsilon xy equal to theta will be equal to the difference will be equal to what is the difference from here to here and divided by del x, right. This is the will be equal to. So here we have del L divided by L, del L, and this is let's call capital L like this. So will be del L over capital L, so which is equal to del L is nothing but this minus this. Okay, so basically what we get is del ux over del y dy over dy. Okay, so L is from here to here, which is dy, and which will be equal to del ux over del y. So we got this one for this case. Similarly, for other case, like when you have like this, say instead of having like this one, now we are giving this like this. So meaning that we have okay. So here this is uy, and here this is uy plus del u. So let's write. So this one is uy plus del uy over del x times del x. Okay, why? Because what is the meaning of that? Here you have uy, and from here to here distance is dx. So uy plus how uy is changing with x multiplied by dx, dx is this length, right? And in this case, again this angle, this is the angle, yeah, this is, say this is psi. Okay, so in this case what do we get? We get epsilon xy will be equal to psi, yeah, which is equal to, again we will do this kind of analysis, and psi will be nothing but this angle will be nothing but del uy over del x. Yeah. Now this is first scenario, this is second scenario. Okay, so this is first scenario. Okay, this is second scenario. Okay, and this is the third scenario. Yeah. Okay, and in this case we have both angles, right? So we have basically theta 1 which was theta here, and we have theta 2 which is psi here. So basically theta 1 equal to theta, theta 2 equal to psi. Yeah. So by definition the epsilon xy is nothing but both of them, right? So this is how we epsilon xy is defined. So epsilon xy equal to theta 1 plus theta 2 is equal to theta plus psi, just to relate to these guys here and here, and basically what we get is equal to del ux over del y plus del uy over del x. Yeah. So, this is how we define epsilon xy and how this the equation is. So, okay, so we understood from where this is coming. Okay, so although this is a repetition again, so for most of you who have studied solid mechanics would know automatically, but still we have done that. Okay, so that is clear now. Now only thing remains is the Newton's law, as we have to find out details about this. If sigma tilde is equal to d tilde epsilon tilde, yeah, then d tilde equal to what for plane strain, okay, plane stress problem. Okay, how to find out? Okay, so we are going to, we will just write okay, so we will first we understand which all things will be there. Okay, so let us say again we are having one element such as this one, where by element I don't mean the finite element, basically the meaning that some square part that I'm getting out of the plane problem. Okay, so something like this one, from here I am taking one a square part from there, just very small, just to analyze. So okay, so we have this one, and then what we want to do is we have the stresses here, right? So we will have sigma xx here, sigma xx, then we have sigma yy, and then we have all this. Okay, so this is sigma xy, right? Sigma xy, all of 4 are sigma xy, and sigma xy. Okay, so we have like this one, and there is a relationship between the these 4 stresses. Similarly, for a strain also we can write as we have a strain xx direction, and then a strain in yy direction, and a strain in y direction, and then we have all these like this also. Yeah, so this is epsilon xy, and all of them will be epsilon xy only. Okay. Now we have to find out the relationship, how sigma and epsilon are related. Okay, so the relationship, how they are. Now if we look at this one, the strain here is the one which we are looking at it. Yeah? So this one is a strain will depends on this strain. So there is no stress in, so this is plane, so we will write here plane stress. So sigma zz is equal to 0. So there is no sigma in the direction perpendicular to this plane, but there can be epsilon zz basically. So epsilon zz is not equal to 0. Yeah. However, if we have if you take plane stress, so I will just also include here for plane strain, sigma zz not equal to 0, but epsilon zz is equal to 0. Yeah, so this is the difference. Okay. Anyway, we are going to concentrate on plane stress only. Yeah, there is a difference that in D basically. Yeah. So, for plane stress we will derive from here in this lecture video. For plane stress D we will derive. For plane strain, please refer to the book. Okay, it is given, D matrix is given for plane strain problem. Okay, so coming back to the plane strain, plane stress. So I was saying that there is a relationship between stress, this strain and this strain. This strain is not related to sigma xy. This strain is related to sigma xx, means epsilon x is related to sigma xx. Epsilon xx is also related to sigma yy via the Poisson's ratio. Okay, so Poisson's ratio is basically the Poisson's ratio and nu, and that is basically if you how the strain. So this will be equal to minus minus of strain in lateral direction to the strain in the axial direction. Yeah. So L for lateral, A for axial. Okay. What I mean to say is, let us say you have a bar and you are applying a, so you have some, you are applying some stress, right. Okay. So because of that there will be a strain. So and let's if you have a 1D problem, then if you apply a force, then sigma will be equal to, or you can say sigma xx. Let's say this is x direction and this is lateral is y direction. Okay. So sigma xx is equal to will be equal to F over A simply, and strain will be equal to epsilon xx will be equal to sigma xx over the E. That is it, where E is the Young's modulus. Okay. So this is what you will get. Will there be any stress in this direction, lateral direction? Yeah. So in lateral direction we will have no strain, so no stress. So sigma yy will be 0. But will there be any strain in the lateral direction? There will be a strain, because of the Poisson's ratio. What happens is when you pull it here, laterally it will contract. Yeah, so there will be a contraction in this direction if you pull in this direction, and this is because of the Poisson's ratio. So the value of a strain in y direction will be equal to minus Poisson's ratio multiplied by epsilon xx. So this is how it is related. Yeah, or you can say that epsilon yy, or you can say that nu equal to minus epsilon yy over epsilon xx. So this is what is Poisson's ratio. Okay, so from 2D, if you understand, we can now extend it from 1D. If you understand, we can extend it to the 2D problem. And how we will do that? So we can relate basically. So think about the, if you are applying a force in a strain in this direction, a stress in this direction only. So we have sigma xx. So a strain in x direction will be directly proportional to sigma xx, right. So we will have this divided by E. Okay, this is something like this one only, right. This is, however, in this case there is no lateral force applied, right. So only we have a strain, but there is no force applied, and hence we have sigma y equal to 0, but in this case sigma y is there. So this is sigma yy, this is sigma yy. So sigma yy alone will produce what? Will produce a strain which will be sigma yy over E. So what I mean to say is the will be equal to sigma yy over E. There will be the Poisson's effect, meaning that a strain in this direction will be a strain due to sigma xx plus a strain due to sigma yy. For sigma xx, this is this one. For this one, because of Poisson's ratio, if there will be a contraction in this direction, if you apply this, there is a extension. If you apply this, there is a contraction, there will be minus. But this will not be equal to sigma yy over E, but rather multiplied by nu, which is Poisson's ratio. Hence, you will have minus Poisson's ratio like this. Yeah. Similarly, you can write for the other way, or you can write epsilon yy equal to sigma yy over E minus nu sigma xx over E. Okay, done. Okay, and these guys don't depend on sigma xy. Okay, xy will not appear. Okay, xy is basically coming from the because of the torsion only. Okay, so what is the meaning of that? Meaning how they are related is as follows. So let us say again we have the analytical element here, and what we are going to do is we are going to apply a tau or sigma xy, right. We are going to apply sigma xy here, and because of that if we have sigma xy like this one, then we will have this kind of things here. So all sigma xy, sigma xy, sigma xy are there. Yeah. So this sigma xy will produce corresponding epsilon xy. So which will be like this: epsilon xy, epsilon xy, epsilon xy, and there is a relationship. What is the relationship? This is simply you may be knowing, or simply you know like this: tau equal to g times gamma, right. So you know where basically this is same as saying sigma xy is equal to g times epsilon xy. Okay. Here also this is shear stress, this is shear stress, this is gamma shear strain, this is also shear strain. Okay. There is a difference between the two though. So this is talking about the engineering strain, engineering stress. Here it is talking about is different, little bit different notation. Yeah, this is called Cauchy stress. This is some term for it, but basically this is the actually same thing. Yeah. So this one anyway, this is not the solid mechanics class. So here for you this is just given basically, and from there we are going to derive it. Okay. Now this is the relationship. What? Sigma xy equal to g epsilon xy, where for isotropic material there is a relationship also. Isotropic material, g is equal to also E over 2 1 plus nu. Okay. This is again comes from the solid mechanics class. For you it is given, just you memorize, it is given. Okay. So g is, this is the shear, this is shear modulus, okay, or modulus of rigidity you call it, modulus of rigidity. Okay. Okay, this is how it is, and this one E is the Young's modulus. Yeah, so this is Young's modulus, and the nu is the Poisson's ratio. Okay. So we have got this. Yeah. Okay. now what do we now we have to just relate. Basically we have got a relationship between the G and E, got sigma xy and epsilon xy, got relation between epsilon xx and sigma xx and sigma y, and similarly for sigma epsilon yy to this one. Then we can write the equation, right. So we can summarize this one as this one, we can write simply in like this one, right. So this will be epsilon epsilon xx epsilon yy is equal to, yeah, and then we can write like this, here one we have 1 over E, and here we have sigma xx, yeah. So even we can take that out, we have basically 1 here minus nu here minus nu here 1 here multiplied by sigma xx sigma yy. Okay. So this what we can relate, right. So this whole this system of equation we can write it like this one, and that we can use. So epsilon xx epsilon yy equal to 1 over E 1 minus nu minus nu 1 sigma xx sigma yy, right. We can, but remember sigma is written as function of, so d is here. So this is sigma equal to d times epsilon, but here we are writing epsilon is equal to some matrix times sigma. So we have to invert basically. So, okay. So then if you invert it, what do we get? We get like this. So sigma xx sigma yy is equal to, and what do we get? We get 1 over E and 1 over E 1 minus 1 minus 1 1, okay, done. And like inverse of that minus 1 and multiplied by epsilon xx and epsilon yy, okay. So which will be equal to we have E value, and then we will have divided by 1 wrong here. So there will be nu 1 minus nu here, and then minus nu and this, yeah, now it's correct. So 1 minus nu a square, so we have divided by 1 minus nu a square multiplied by then we have this and this interchanging, we will get the same thing. So 1 1, then negative becomes positive, so we have nu and nu, right. So like this, and then we have epsilon xx epsilon yy like this, okay. So this is what we get, but one thing we forgot, we also have sigma xy there. So we write here sigma xy will be equal to, we know that this is equal to G times or E over 2 1 plus nu, that is the G, times epsilon xy. Okay, so this relationship already is given like this one. So we know that, so we can take from here. Now we combine them together. If you, yeah, so if you combine them together, then what happens? So we can see combining them together. Okay. Combining, what we get? We get like this. So this gets sigma xx, sigma yy, sigma xy will be equal to okay, and then we have E common. So, we will have E common, right. So, we will write and here we see, here we have 1 minus nu a square. So, we can write 1 minus E over 1 minus nu a square as a common thing. So, we can write like this. So, E over 1 minus nu a square as a common thing, and then we have nothing but 1 nu. So, 1 nu 0 nu 1 0, right. Okay. Now, next is this. Okay. So, we are going to write here this is equal to epsilon xx, epsilon yy, epsilon xy. Yeah. Okay. Now, this is done here because we have directly taken from here. So, this is done. Now, we have to fit this one, and how to fit. So, we have sigma xy here, this is g. So, now what we know is this value will be 0 and only this value will change, and what will be that value. So, we have to have something here so that this multiplies by this to get you this one. Yeah. So, that means this already have common E here. So, E here, then 1 plus nu is there. So, here 1 minus nu will be one thing, and then 2 is here. So, if we have like this one 1 minus nu over 2, okay, if you write like that, then what happens? We multiply by this 1 minus nu. So, this becomes 1 plus nu, then we have 2 here. So, this becomes 2 1 plus nu, and then like this one. So, what we have? 1 minus nu over 2. So, this is what, this is the D matrix basically. So, what we found is 1 nu 0, D matrix will be the whole thing like this one. Yeah. So, basically we can write it nicely now. So, D tilde will be E over 1 minus nu a square, and then we have 1 nu 0 nu 0 1 0 0, right, then 1 minus nu over 2, right. So, this is D, okay, and this we are getting from where? The epsilon, sorry, sigma tilde is equal to D tilde epsilon. Yeah. Okay. Yeah. So, where D is given by this one, and this epsilon is also given by the D tilde times del S tilde times U tilde. That is what this one is. Yeah. So, this is how the whole sigma will look like. Now, this we can put in the put this in the weak formulation. Okay. So, final weak form, how will it look like? The final weak form will look like this. So, gamma t, then w tilde t, t tilde d gamma minus omega, then we have del S, then we have w tilde transpose, then we had sigma. Now, sigma we can write as D tilde E, and even better we can write like this one. Now, this has U term now. So, we will have D tilde and then del S U tilde. Now, it makes sense because you see here this had del S W, here you have del S U. So, you know that it appears, you know that W and U both appears inside it. So, we have there. So, that is good. Okay. And then we have d omega, okay, minus omega w tilde t b tilde d omega is equal to 0. So, this is our final, the final a weak formulation, and the next thing is to solve it basically. Yeah. So, this is the final weak form. Okay, this is the final one.